Okay, let us continue. Here I found the notes I used to calculate this demonstration program, just to sort of be a little bit more familiar with all these strange matrix expressions. So for this demo problem, 2x2 equation system, you can actually calculate wherever you want. And a little bit messy, of course, but still quite possible here to calculate it all the way through. So here you actually have clear expressions then. What are these different matrix products? And what does actually this function looks like when you program it like this. So finding here in general a functional can be quite tough mathematically to be minimized for then solving the corresponding equation system. Not necessarily so easy. Not that you have to do it, but here I wanted to have a sort of a graphical image of it. I wanted to just to see how what it looked like. And then the steepest descent method. Again, here you can now actually calculate these different products and see exactly what you get. So here actually no surprises. Remember alpha, sort of determining how long should your step be, assuring that you are still walking downwards. So fairly straightforward. Then finding the new x values based on the old ones. For the conjugate gradient, a little bit more tricky with this orthogonal directions. Not so easy to see what they are. Still possible, of course, to calculate it, which I've done here. So not so easy to see that, this was a very smart direction to use. Not easy. But, I mean, that's a job for a mathematician anyway. I mean, we as engineers, we need something that works. I'll put out this one out for you as well. Just attach it to one of these PDF files I think you have gotten already. So now for the comparisons. Where was it? Here somewhere. A MATLAB program. We try our classical model problem here. Poisson equation equal to -1. And it's a two-dimensional, so physically it's a square duct. And we are seeking out this laminar parabola solution. And if we now start, just for fun, I say I have a 4x4 problem. And then I define a matrix, which then equals, what should we do? Zeros, like that. And then we set up the coefficient matrix A. So here we create our full matrix. Here I've done it rather stupid, straightforward. You have now more clever commands available in MATLAB, because this A matrix is going to be quite the diagonal matrix. So I can show you, if we run this one and crush him, the A matrix now should be a 16x16 matrix and should then look something like this. So as you see, the discretization star, if you can recall, double derivative in both directions. You will have minus 2 from each of the two different derivatives altogether, delta x equals delta y, you will have minus 4 on the entire diagonal. You're using the neighbors. Not all of them, because remember, you're hitting a wall sometimes, and then we're going to the next line and so on. So occasionally some zeros here. And then also you're using the one above and the one below. And there you will find some way out here or way down here. So this, yes, typically will be your A matrix. And as you see, most of it will be zeros. And if you want to have a peek how it looks, when it gets really big, you use a program called SPY. SPY, that gives you a graphical image of your matrix. He shows you only the elements different from zeros. So clearly here it's rather stupid to store everything. And if you now look at the memory, for a 4x4 problem, you have a 16x16 matrix, which then requires so and so many bytes, which is not so funny. And then we start increasing our problem. That was 4, so if we now jump to 40x40 and do the same. A 40x40 problem, we have 1600 unknowns, but the A matrix is going to be 1600 by 1600. And how many bytes do we have here? We have 20 megabytes. So he increases squared. If you want to have a peek how he looks, you can still do that. But now you will see he appears to be 3 diagonal, which is a lie. You don't have 3, you have 5. If it had been 3, then the problem is trivial. Then you solve it directly using Thomas' algorithm. But with 5, no, that's not allowed. That's not possible. If you zoom in here and zoom in, you see you have 3 very narrow and then a couple in addition. And for this computer here, how much can he take? I'm not sure. 80? Yeah, he can do it. Who's 300 megabytes, okay. I have bigger number on my keyboards. Let's see. The limit should be somewhere around here, I think. You can stay. 90 was okay. Okay, 100. Wow. Still making it. 800, okay. I'm getting pissed. Well, he still claims he can do it. But you see for yourself, this is, I don't think I should try to run this program now. I mean, he will blow the memory. And sadly with MATLAB, if you blow the memory, strange things will happen. You have to reboot the machine typically. So it's not that smart. So what do? You don't store all the zeros. The size here is way off. So 200, I mean all these bytes, and most of it is going to be zeros anyway. You store it as a sparse matrix. So if we now Still using 200, but I just defined the A matrix as sparse, but everything else as before. If we can recall this number, how big is it? 1, 2, 3. 1, 2, 3. 1, 2, 3 should be 12.8 gigabyte. Okay, so now let's run this one again. Okay. And then you see what happens. The size is the same, but we have reduced it now down to 35 megabyte. To see what's going on, I can go back to the first one, only 4. And then crash him, and then show you what does this A matrix looks like. Now it looks something like this. So you see, he stores only the positions where you have something different from 0. You need the indexes and you need the value, of course. But this will create a lot of less memory used. Still, nothing has changed. The logic, your program will be exactly as before. So you could use this matrix A exactly in the same way, but he's just stored differently. This is not something peculiar for MATLAB. You find this in any computer language. They will have this sparse technique, of course, or else you blow the memory very, very fast. So the rest of the program, you just continue as if you had a full matrix. If you want it to be full, you could do it. So you have something called, say, A equals full of A. Then he will be not sparse anymore. Then he will be back to this form. And then you could write A equals sparse A, and then you can mix between these two if necessary. So sparse, very, very good idea. So here, that's the pause. That's where I crashed the program. Now for the rest of this program, we are going to solve the equation system several ways. First, here I want to have an exact numerical solution. So here I used the backslash. That's the built-in MATLAB solver, which is very efficient. Coming back to that later, just so we have something to compare with. Furthermore, I have an exact analytical solution for this problem. So something that I stole then from Årset when we were dealing with multigrid. We used this model problem, so we have an analytical solution there, just for comparison. And then we now starts to solve it using different methods. So here you'll have steepest descent. 3 lines. These 3, that's the steepest descent for you. And then I just put into the results using the norm for the difference from my solution now versus the exact numerical solution and versus the correct analytical solution. That's 2 different things, of course. And here I try to take the time, how many seconds it takes to calculate. Then we do the same, but now with conjugate gradient. So here then you need a couple of more lines. So this is the entire conjugate gradient method. Conjugate gradient alone. And also this one. Then I have played around with SOR. So I have done several simulations before and then finding a good omega. So I just interpolate here depending on my choice of the number of unknowns. So here you have the classical SOR. Rather straightforward. And what else did I use here? Gauss-Seidel, of course. It's just SOR with omega equal to be 1. And then I have played around here with something called BCG stub. That is a conjugate gradient. Now using a preconditioner. So let's try to run this one and see how they compare. I only have 4x4, don't I? Yeah, that's a little stupid. Let's give him 100x100 or something. Here we go. Let's look at the relative error first. So the relative residual, that is where you can go bananas and solve it all the way down to machine accuracy. You solve your algebraic equation system perfectly on your computer, if possible. So you see the first one here, the number of iterations, that is this BCG stub, conjugate gradient with something in addition, and he is so fast, he is almost unbelievable. So he hardly uses any iterations at all. Then we have conjugate gradient. It's this one, and you see conjugate gradient alone actually beats SOR with a fairly decent omega. So conjugate gradient will be faster in general, yes, than in the SOR. Gauss-Seidel and steepest descent, all the way up here. You can sort of forget them. You'll never find a solution, not with 100x100 problems. Well, you will, but you need a tremendous amount of iterations. Now an important point. Working your way all the way down here to machine accuracy. Yes, you can do that, but why should you? If you look at the other graph, comparing now with the exact analytical solution, you can't hope for any better accuracy than your mesh. So I mean, remember, you have a second order accuracy in the mesh. You can't get the solution better than something like 10 to the power of minus something. So don't waste time on too many iterations. So here we see sort of the same. This BCG stub, he has only 1 point. He has done one, but it actually involves several iterations. But it's hard to get printouts actually what he's doing. He's rather complex. For the conjugate gradient, still beats our SOR. And the old-fashioned ones, you can easily forget them. So here is, of course, a question: where would multigrid be? Well, actually, he should be actually better than this one, or fairly close to this one. I haven't programmed that one in here, so this BCG stub. What has he done? Well, he is the ordinary conjugate gradient method, but with a preconditioner. So to use him, you first have to set up your preconditioner. You are sort of using this M inverse that should be close to A inverse, or not close, but at least on the way to A inverse to speed up the solution process. So I had to call him here first using incomplete lower upper. MATLAB has changed the syntax, so I had to reprogram it a little bit, but at least this one seems to be working. Now this L2 and U2, they will be matrices that is used inside the solution algorithm for your coefficient matrix A. So you can now check the size here of this L2 and U2. That's sort of on the way to find A inverse. So this one, that was the lower, and if we zoom in a little bit, say up here, you see how he works. So he's clearly a lot of zeros, but he has a couple of bands that he's going to need. And the more band, the wider these gets, the more memory it requires, of course. So here it is it's a danger if you want him to be too accurate, then this one is going to be too big. So we can try it if we redo it here and say to do accuracy here -10. Let's try it. Still get the same results, and the B-Segestab, now he looks even better, but at a certain price. So if we now do this SPY L2, doesn't look that bad actually, but if you zoom in, roughly the same actually. Too bad. Let's check the other one. That was upper 2. No, that looks roughly the same. I think there's more into it here than we can see actually, but you see you need several bands. So the width of these bands that's needed, that's the price you pay in memory. I'm not sure if these are sparse now. Let's check. Where are they? Yeah, they're sparse. And you see, that might be better to see it here actually. Our coefficient matrix, very big, but don't require much storage. L2 requires a lot, and U2. So that's where you pay the price. Now the method, conjugate gradient method, will be very efficient if you can do it. So you have to pay attention here to actually what you are doing. It should be possible, say, let's take a very bad one here then, -2. Do a rerun. Yeah, so now you see the B-Segestab. He's not so efficient anymore. So now I have a very small L2 and U2. So you see now they are hardly well, on the same level almost as my A matrix, but then again the conjugate gradient method not so efficient anymore. He had to take many more iterations. And if we have a peek now, spy U2, it will be much more narrow. If you now zoom in and check how many bands do we have here, we don't have that many at all. If you want to play around with this in MATLAB, yes, you can do that. Duck, what is it called? BCG stub. You find the descriptions in MATLAB, and not only this BCG stub, you have several of these. So here you can read a lot if you want about how it's done. Jump down to examples, how to use it, and here using with a preconditioner. I mean, clearly it's a preconditioner that's very important to speed up the process. So that's something you have to do if you're going to use this method efficiently. So here you see you have something that explodes, so the residual blows up. So if you use them wrong, very bad idea. So you have to know a little bit what you're doing here. And down here, see also, and then you have a whole bunch of these different methods. Well, not that many, but at least these three here. Here you have one as well, and I'm not familiar with him. So you have several at least. So feel free to play around with them if you want to use conjugate gradients. The theory behind them can be complex, can be tough, but with MATLAB and these examples that they normally provide us with, then should be absolutely feasible at least. Any questions so far? Let's see, I had some other demos here as well, didn't I? Not that one. I just wanted to check MATLAB because they normally would say use this backslash. I mean, you have the inv as well. So I can show you here, look, inverse of a matrix. So yes, you could use it. Inverse, then you have solved the equation system, but they say /b is computed totally differently and is recommended. And clearly it is recommended. I can show you here. Going back to the first one. 4x4 problem. Run, and then we had our A matrix. It was now sparse and looking something like this. And if we now write A equals full A, not with big F, like that. Yes, we have the A matrix. And now we solve the equation system. Okay, then I'm going to need equation B equals inverse of A. And you see that is the price. An inverse matrix is a full. Even though our original A matrix, he was, well, very nice. only 5 different diagonals, still the solution will be extremely memory dependent. So an inverse matrix, no, that's not something you want to store. You can't store it when it's a big problem. Instead, we play around with the backslash. So here I now have tried with different number of unknowns, and then try to solve the system. Let's just run this one. Shouldn't take too long, I think. So it starts at least very fast, but for the big ones, 150, 175, and finally 200, he is starting to use on some seconds. So remember, this is a 200 by 200 problem, so you have quite a big equation system here. So this is sort of disturbing in my view, because I mean MATLAB, come on, that's the slowest, worst possible language you could use. It's used for illustration, for teaching purposes. You never write a heavy program in MATLAB, of course not. You use C or Fortran, something. But the way they have done it with the backslash is pretty genius. If you here look at sort of the number of unknown versus the CPU required to solve it, it's actually a straight line, more or less. Little curved up, but not much. So he solves it very, very fast. They have done something quite ingenious in MATLAB when they have constructed this backslash algorithm. And if you want to read about it, you can have a look. The examples is quite okay. But if you want to have a peek into the actual algorithm, what they are actually doing, it's heavy, very heavy indeed. So they do a lot of checking, testing before they actually decide how they should solve the equation system. Furthermore, they solve it without blowing too much of the memory. And let's look at the printout here. The final printout, just for the final case. You can tell the backslash actually to provide you with information. What are you actually doing? And you see he has done a lot of testing here. Checking bandwidth, is it in a diagonal, pure diagonal, the density of the different bands, and so on and so forth. So they have done a lot of testing, and then finally decide, okay, let's use this algorithm. And there, I don't think you find the source code for for these routines. They will be as DLL, I mean, or MEX files. They will be executables. I mean, if they had been in MATLAB also, this will take forever. So using backslash in MATLAB, that's not a joke anymore. It's really, really fast. So it's absolutely quite impressive. And he doesn't really blow the memory too much either. So no, I'm quite impressed with MATLAB. So don't be embarrassed if you use MATLAB. You can say, I know I'm using backslash, and then you can be proud of yourself. Okay, that was sort of a sidetrack. But then this actually means if you have a problem, and it's a big one, and you want to solve it efficiently, you can actually use MATLAB and the backslash. It will be quite efficient. You can hardly find anything that can beat him. So they have done a very, very good job. So I don't think we can get the source code out of these guys. We've been talking to, what was he called? Clive Moller. He's one of these gurus creating MATLAB. And we asked him, for instance, for this optimization solution, the fsolve, not the f0 that can find just for one variable, but fsolve he can find for many variables. And ask him, please, couldn't you put that one into the ordinary MATLAB instead of having it in an optimization toolbox? He just smiled. He wanted money for it. So I don't think you can get the source code out of this, but I mean it's fairly decent documented. So you could have a peek for yourself if you're interested in the numerics behind it. And I think you'll find also references, articles, how they have done it. How they've done it in practice, no, I don't think you will be able to get the source code there. That said, let us jump to Google. So if you want a fast solver in any language, you just print it in here, and yes, you'll find a lot. You'll find a lot. One was called PETSC. PETSC. I think it was. Yeah. Should be here somewhere. So you can find plenty of these libraries, source code banks for actually anything. And here within PETSC, actually you could find conjugate gradients, multigrid in, what was it, at least Fortran. And I wonder also you find it in C. So just as an example, if you search for anything else, say conjugate gradient, which language do you like? C++? Code? You should be able to find a lot. So whatever you need, don't write it yourself. Find it. And even MATLAB. No, not MATLAB. Sorry, multigrid. Multigrid, which then is supposed to be the best. Yes, you can find clearly several routines for it written for you, but then typically either they have taken a model problem, Poisson problem, 1D, 2D, but if you have sort of a general solver, then you are talking what we call then the algebraic multigrid. If you just want a multi-purpose solver, then you have to use something like this, unless you have one specific problems that somebody else also has solved. So the algebraic multigrid, that will not be as efficient as one written for a particular program, but it will be fairly decent, I think. Anyway, you'll find whatever you need. It's out there. Just search for it. Okay, that ends today's lesson, and that ends also what we are going to do about fast solvers. So we stop here. Tomorrow then, finite volume, unstructured mesh systems. I will put out some more for you. So we stop a little early. Any questions? No? Then we stop here.